My name is Jason Barrera. Today I'll be giving you a speech about Neutron Stars and Pulsars. This is my audience, the 536 and Port Maintenance Company. And I'm going to give you a little story. Before we deployed, I lived in Waipahu, and my wife would, at nighttime, she would stare at the stars. And she told me that there was one star that just kept blinking constantly. So I'm like, okay, airplane, helicopter, something like that. But the next day, it was still there, so I got kind of interested, started looking it up. And apparently, some stars, when they die, they refuse to stop blinking. So we have a picture right here. Anyway, this picture is courtesy of Mr. Barrella's astronomy blog. It shows the life cycle of a star, or actually the death cycle. Today we're going to cover what a neutron star is, what is a pulsar, and what is the likelihood that we will see one of these events. My main sources is NASA's Imagine the Universe website and Harvard's Chandra X-ray Observatory website. So first off, you can see here, at the end of a star's life, we have three major groups. We have smaller stars, medium, and large. The smaller stars, such as our Sun, will begin to expand once we run out of hydrogen fuel. Towards the end, it'll erupt. It's pushing all the gas away and become a planetary nebula. Afterwards, it will shrink down to within 1/1,000,000th of its size and become a white dwarf. The final stage for our Sun is very dense. In fact, to quote Chandra Observatory, an object the size of an olive made of this material would have the mass of an automobile. On the heavier side, we have the massive stars between more than 8 times the mass of our Sun. They'll do the same thing, they'll expand just a lot bigger, and when they explode, they call it a supernova. It's much more intense. None of the stuff hangs around, it's gone. The mass of the super heavy stars is so great that it exceeds 186,000 meters per second for the gravity, which means light cannot even escape. So we call these black holes. Now the star of our show, pun definitely intended, would be the neutron star, middleweights, between 4 and 8 times the mass of our Sun. They go through the same road as the massive stars would take, going to supernova, but they don't have enough mass to keep all the light inside for that gravity. So instead, at the atomic level, the positively charged protons and negatively charged electrons actually fuse to make neutrons, hence the star's name. So the whole thing is made of just neutrons with no charge. And as you can see on here, the neutron star seems to have flares of energy coming out inside. Look at this picture from NASA. The neutron stars, because they have no charge, their magnetic fields are just crazy. And pulsars have spin so fast, these magnetic fields, according to NASA, 1 meter of energy in the magnetic field has more power than humans have ever generated on Earth to date. This magnetic field has the ability to channel the star's radiation out through the poles. How that works is, while the pulsar in this picture is spinning left to right, the energy is being diagonally shot out. So from Earth, when we see it, it's like a lighthouse effect. The beam is constantly on, but only when it sweeps into our view will it shine. It turns off as it goes. So let's talk about this kind of radiation. We put out 4 types. Radio, optical, X-ray, and gamma ray. NASA states that the faster a pulsar is turning depends on or determines the amount of radiation and what type. As you can see, we have the crab pulsar, puts out a lot of radio waves, a few optical waves, X-rays, gamma. The middle one, 1509, it's not spinning fast enough to put any optical light, so you won't be able to physically observe this. And the Barrera pulsar, it's putting out a lot of optical light. So let's talk about what's the likelihood that we'll be able to see one of these with our naked eye from Earth. NASA claims that in 2010, there were 1,800 observed pulsars through radio telescope. However, only 70 of these put out optical light, and even fewer are close enough that we can view without the aid of a telescope. The best areas to observe will have low cloud cover at night, low city lights, stuff like that, which fortunately for us in Hawaii is ideal conditions. In fact, the Mauna Kea Observatory is the largest observatory in the world. It sits 44,200 meters above sea level on an inactive volcano on the Big Island. And this is where astronomers for 11 countries come and collect the best research data, with the entire observatory being able to take in more than 60 times the light that the Hubble telescope can. So in conclusion, today we've learned what a neutron star is and how they differ from other star endpoints, and the characteristics of neutron stars that label them pulsars, and the likelihood you will spot a pulsar from Earth. So I'm sure we're already way past ready to return home to our families and get back to our regular lives. I'd like to suggest that you take a few minutes out of your time, just look up at the stars, and think of the great events taking place far from home. This concludes my presentation. Thank you for your attention.